Section 442, example 7. This example has an initial electric field, which I'll represent with field lines. I'm not going to draw the middle yet, of intensity E naught pointing up. Okay, E naught vector, actually. And what we do here is kind of like example 8 in chapter 3, so I'll write that here. We're bringing in a sphere, but this sphere isn't conducting. This sphere is actually a dielectric, a linear dielectric. I'm pretty happy with that. And as you can probably guess, you're going to get some electric field going through this sphere. Boop, boop, boop. Magnitude E. And then the things around it are probably going to bend around in some interesting configuration, depending on whatever happens inside there. So the question is find the field inside the sphere. If this were a conductor, it'd be easy. The field's 0, but it's not a conductor, it's a dielectric. So we have to use the tools that we have available to us. One way to approach this problem, and it actually works for this problem, is you say, well, if we have an electric field inside the sphere of E naught, what's the polarization of the sphere? So we can write the polarization of the sphere due to E naught is going to be, it's a linear dielectric, so epsilon naught chi E of the initial electric field. And then the question is, what is the electric field produced by that polarization? So I'm going to call this E1 is produced by the polarization. We solved this problem back in example 2 of section 421. We get negative 1 over 3 epsilon naught of the polarization that we just produced. Okay? And that's going to be equal to, and plug in this original term here or there, we get minus chi E over 3, the susceptibility divided by 3 of the original electric field. So if you were to see what this new electric field would produce in terms of polarization and what the resulting electric field from that new polarization would be, you just basically do what you just did, and you end up with negative chi E over 3 squared times the original electric field. And the idea is that you're going to add up all these fields on top of each other using principles of superposition. So we're going to take the sum of all these electric fields from 0 to infinity, and we're going to get some answer. Now, looking at this, this is a geometric series where the number itself is less than 1, so we can just apply the simple rule that this is equal to 1 over 1 minus chi E over 3, the thing that we're taking the exponential of, times the electric field. Okay? That's the geometric series result there. So another way to write this could be you multiply top and bottom by 3, and you get 3 minus chi E. Well, you know, k is equal to 1 plus chi E, so that's the same as 2 plus k times the original electric field. So this turns out to be the resulting electric field. After doing this an infinite number of times, you get the electric field that you end up with. And if you're not happy with that solution, then what we can do is we can say, well, what's the resulting polarization from this electric field? So let's calculate that. So the polarization is going to be epsilon naught chi E times the electric field we just calculated. 3 over, let's do 1 over 1 minus chi E over 3 times the original electric field. And what's the electric field this produces? Well, that's going to be negative 1 over 3 epsilon naught of this junk. So that gives us negative 1 chi E over 3 times 1 over 1 minus chi E over 3 times the electric field. And the question is this a resulting electric field? Does this change the field at all? So really we want to see if this is 0 or non-zero or what it is. And so, let's see, how did they do this? They kind of made these numbers dance all around. No, okay, so we get chi e over 3 minus chi e. So this is equal to minus chi e over 3 minus chi e. And so if we combine that with the background field, you recover the field you started with. So, and so you add in the background field there. So the new electric field plus the electric field equals E naught minus chi e over 3 minus chi e epsilon naught. And that is going to be 1 over 1 plus chi e over 3 of the original electric field. So the resulting electric field from adding in additional polarization due to the electric field we just calculated is basically nothing. It doesn't amount to anything. So we've kind of reached a stabilization point where, you know, doing this additional times doesn't get you any different of an answer. So the interesting thing is this only works for spheres, it works for ellipsoids, and it works for cylinders. So it doesn't work for cubes or different shapes like that. And the reason why is because as you apply the polarization due to the electric field, you get a more and more complicated field and polarization inside of the object. And it's not possible to really see where it goes after applying it several times. It just becomes infinitely like a fractal. So not really useful. Anyway, hope that helps. Take care.